Also, before we get started, I'm just probably gonna say this every single day, but okay. One of you guys said that you can't find the recording on the website. I have to be honest, completely honest, I haven't really checked the website lately, so I can try to find it, but otherwise I'm just guessing that they haven't uploaded it yet or anything like that. But I think they'll probably be able to find it sometime in like uh near future. So here's the panel. If that would be chemistry. So there's a recording for the first. Okay, the recording should be here. Um, so that would be day one and day two. And if you can't find it, it would be under you go to 2023 summer camp program and then to 2023 summer camp resources. And then you would basically just pick what you want. So these are the classes that we're teaching for this summer. And you can go down. So for example, instead of chemistry, you want to see the recording for biology. Um, you would go over here and you can find all the resources, so like homework, outline, slides, etc. I think over here, yeah, so it says like there's some resources, however, I think only the slides should be available. All right, so since it's 2:02, I think we should probably get started, but other than that, if you guys have any questions or like comments if you don't understand anything, want me to go slower, faster, etc. Oh, sorry, my bad. Um, just don't hesitate to go put it in the Q&A or in the chat. I think you guys should be able to chat with everybody. Um, but if there's anything you guys need, just let me know. All right. Okay. So today we're going to be talking about. Wait, let me put it in the presentation mode first. But today we're going to be talking about inter and intramolecular forces. So let's just get started with that. So, in a molecule, so for a molecule is formed when two or more atoms join together chemically. So, for example, you have water, which is where two atoms of hydrogen and one atom of oxygen. Wait, hold on, my bad. Sorry. Um, okay, wait. Let's just use a different example because I feel like I just had an entire brain fart. Say you have sugar, like the kind of sugar that you would, um, like glucose, for example. That would be a combination of carbon, hydrogen, and oxygen. So this is basically formed when two or more atoms. So in this case, for sugar, it would be 6 plus 12 plus 8, 6 plus 12 plus 6, which should be like 24. So that's when 24 atoms join together chemically. And this will form a molecule or like a molecule. So diatomic molecules, which are molecules with only two atoms of the same element, can sometimes be confused for atoms by themselves, but these are actually like two atoms bonded to themselves. I don't have any pictures over here, but if you guys would want any pictures, just let me know. So for example, over here we have H2, which is two hydrogens, and O2, which is atmospheric oxygen, which is basically all oxygen, but instead of just one oxygen atom floating around, it's two oxygen atoms bonded together. Okay, before we get to that slide, can anybody tell me what the difference between intermolecular and intramolecular is? I guess you guys can put it just in the chat. Or if you don't know, just say you don't know, and then I can like go ahead and explain it, but I guess I'll give you guys a minute to answer that question. And also, if you guys need me to repeat anything, I'm happy to do so. All right. All right. Instead of that, I think I don't want to really waste any time. So yeah. Intermolecular and intramolecular. So if you guys can probably see that inter and intra are both prefixes. So what intra means is like together, while inter is more like between, or intra is within. So if you guys have ever thought of like the interstate highway, which is between, it's a highway between states. So if this one you can see a little bit more clearly, over here the direct one is intramolecular holds atoms together in a molecule, while intermolecular attract um, means attractive forces between molecules. So in this picture down here, you can see that each of these hydrogen bonded to chlorine or hydrochloric acid molecules are have interaction between the molecules in the substance, but they also have an interaction between the actual atoms. So over here, you can see that these two, this molecule of hydrochloric acid and this molecule of hydrochloric acid has are like interacting, while the hydrogen and the chlorine in itself are also interacting. Oh, okay. There. So next we're going to talk about phase changes. I feel like my slides today aren't in the best order because we're going to go deeper into that and more towards the end of the presentation. But a phase change is basically, as you can probably tell by the name, is when a substance changes phases. So for example, a solid to a liquid. However, during this, the molecules remain intact. So there's no breaking of any like chemical bonds, no reactions happen, and these are the changes in state are due to changes between the molecules, so like intermolecular interactions rather than within the molecules, which would have been intramolecular. So for example, you could say this is probably the most basic example ever, but you could say it would be, say, like water freezing to ice and then like melting again and then going and like evaporated into water vapor. So throughout that, the water stays water, right? So the water molecule actually remains intact. All right. So some measures of intermolecular forces include boiling point, melting point, enthalpy of vaporization, and a change in the internal energy of the vapor. So basically, these are just ways that you can measure what has happened or what's going on, or like how much of the intermolecular forces there are. But honestly, I don't think this is as important to what we're going to be talking about today. Okay, so here's some more vocabulary that I think. So ions, if you guys were here for the class, I think on Friday, I think, yeah. If you guys were here on Friday, you guys would have known about ions. I did go a little bit deeper into the ions yesterday on Friday, but essentially they're just atoms that are charged because they've either lost or gained an electron. Um, Dipole, it might be newer in terms of this class. So a dipole is a pair of equal and opposite electric charges separated by a small distance. And these are usually in polar molecules. And polar, also, I'm sorry about the background noise for like the sirens and stuff, but they're the covalent, dipoles are usually like covalent polar molecules. And you guys will probably be able to see that more clearly in the next couple of slides. Or not, in later in the presentation. So these are solubility rules. They're, in my opinion, very important to remember. And they're just like very helpful throughout if you guys continue to pursue chemistry, etc. But just these are the compounds that make something soluble or insoluble. So for example, NO3 salts are soluble, sodium, potassium, ammonium salts, chlorine, bromine, iodine, and like sulfuric acid are should all be soluble, or any compounds with these molecules. However, the molecules over here do not always have, or are not are not soluble. And basically these are just rules that you can follow by, and then the purple are like just exceptions within that. But I guess I would say that this is pretty important to memorize, so you guys can take like a screenshot or write it down. But I'm gonna say these are very important to remember. All right. Okay, so next we're going to talk about electrolytes. An electrolyte is something that conducts an electrical current. So something that you guys might have heard of a lot or seen a lot is that if you've ever gotten like fancy water, like smart water or like sparkling water, you guys might have seen like enhanced with electrolytes for taste. So what an electrolyte actually is that it's something that conducts an electrical current. Like a current in water. So, for example, salt. So basically, the electrolytes would be separated into three groups. There would be strong electrolytes, weak electrolytes, and non-electrolytes. And so, in strong electrolytes, molecules completely dissociate in water. So basically, dissociation means when molecules separate or split things into such as salts or complexes, while weak electrolytes only partially dissociate into ions, and non-electrolytes are just like they completely don't do anything. But how I like to think of it is that like um, it kind of, since it conducts an electrical current, strong electrolytes will conduct a current really well. For example, as you know, salt water is very conductive. However, acetic acid mixed with water is not as conductive. And water is conductive, but not it's just like not very well. And yeah. So next we're gonna go on to the actual interactions between molecules, and this again would be intermolecular forces. So first over here we have dipole-dipole interactions. So dipole-dipole interactions are forces of attraction between polar molecules. So these are effective only when the polar molecules are very, very close. And as distance increases, the strength of the bond increases. So I don't have a picture over here, but I think it's probably easier to understand it if you do see a picture. So I think I'll just pull up one really quickly. Just go to a new tab. So over here you can see that the dipole, which is a pair of positive and negative charges. Over here, this would be the negative and positive. So the positive and the negative are attracted to each other, while the, say, positive and positive would be like repulsed from each other, and that same thing goes for negative and negative. So these would technically be sort of like a bond in something such as water. All right, so let's go back to the presentation. Okay, let's just move this out of there. So as if these molecules are more polar, then the strength of the dipole-dipole interaction would be stronger. And also again, if easy way to remember these are that if these interactions are between a dipole and a dipole. So next is hydrogen bonding. This one may sound a little bit more familiar. Essentially what happens is these really only exist between hydrogen atoms bonded to fluorine, nitrogen, oxygen atoms, or fluorine, nitrogen, oxygen atoms bonded to hydrogen atoms. So for example, over here, this is water again. So here's the oxygen and then the two two hydrogens. We'll just use this one instead because it's labeled, but the oxygen and two hydrogens, and then the oxygen over here. So in this case, the hydrogen atom is bonded to the oxygen atom. However, that doesn't mean that like that's a new chemical. It's like these are bonds outside of like chemical outside of different molecules. All right, so hydrogen bonding in water is pretty important because it's basically if you to repeat what I said in the previous slide, it's basically a hydrogen bond covalently bonded to like a more electronegative atom. Again, we talked about electronegativity on the first day of this class. So these are often found in water molecules, and a lot of water's like specific properties or like what really makes water special is due to these hydrogen bonds. These are weaker than ionic and covalent bonds. You can see that they're between molecules rather than actually making up these molecules, and they break and reform very easily. Okay, next are ion dipole interactions. So you guys know what an ion is. It's a charged atom, while a dipole is a pair of positive and negative charges. So this would be a interaction between an ion and a polar molecule. So for this one over here, and so a negative ion would attract the positive side of the polar molecule because remember, positive and negative go together. While a positive ion, so such like a cation, would actually attract the negative side of the polar molecule because negative and positive go together. All right. These are also weaker than these are well, okay. These are should be weaker than the dipole-dipole interactions. So next, these are ion-ion interactions or ionic bonding. These are the strongest of the forces, and they include one electron being given away. So for example, over here we have sodium and fluorine. As you can see, talking about the valence electrons, the sodium only has one valence electron, while this fluorine has 7. So the sodium wants to give away its one valence electron so it can have a full octet of valence electrons, while the fluorine really wants one more so it can have the full octet of 8 electrons. So in this case, the sodium will give away its one valence electron to the fluorine, and it will form an ionic bonding. Okay. I think this should be the last one of the interactions that we're talking about today. So this is the London dispersion or force or van der Waals forces. These are the weakest of the forces, and they result from when the electrons in two adjacent atoms occupy positions that make the atoms form temporary dipoles. So I know that might sound a little bit confusing, but here's the picture to help. So you have this one atom, right? It's a temporary force that makes all of these electrons go over to one side. And once they've gone over to the one side, you can see that this side is now positive while this side is now negative. Also, just to ask, can you guys see my mouse or should I do the pointer? Oh no, okay. So I guess I'll do the laser pointer just in case you guys can't see my mouse because I'm pointing to stuff. But over here, this side is positive while this side is negative. And if you guys remember from before, a lot of this stuff has to do with this positive negative interaction. So the positive and the negative go together while so these two will sort of do this like little bond thing. This is definitely the weakest out of the ones that we talked about. Okay, now we're going to talk about heat capacity. So this is a pretty important thing to things such as water. So it involves the specific heat or amount of heat that must be absorbed or lost before a liquid or a substance actually changes temperature. So for example, water has a high specific heat, and that makes water very special. So for example, like another liquid, say maybe milk, it would be easier to boil or would take less to heat to boil rather than say water. Um, so basically, um, what this means for water is that it can absorb a or release a large amount of heat while only changing slightly in its own temperature. Next, there's heat of vaporization, which we'll talk more about later in the slides, which is the cooling of the surface occurs when the liquid evaporates. So when water boils, as the steam leaves the water, it takes the heat with it, and then the water cools. What this is really special about to life, so all of these interactions are actually very important in biology. So when your body sweats, this actually can cool you down because when the sweat absorbs off of your, when the sweat evaporates off of your skin, it will take some of that heat with it and allow you to cool down and um, not feel as hot. All right. I think that should have been a slide after this one, but here are the properties of water. So water is actually made out of three molecules. If you guys didn't know that before, would be one oxygen plus two hydrogens over here. So some things that are actually very special about this is that water is polar. So see, compared to this carbon dioxide molecule right here, you can see that this is very symmetric. The two oxygens on the side of this carbon are on opposite sides of each other. Well, in this one, which is also another molecule with three atoms, it's more in a like, say, triangle shape. So these two, uh, so the hydrogens, the would be on one side rather than being like on opposite sides compared to each other. So basically, if this carbon in the middle was a oxygen and they just like change these into hydrogens, that wouldn't work because of like the charges. Again, this would technically be like a dipole because it's a pair of positive and negative charges. So this end would be like a negative end, while um, this end of or this side of the molecule would be positive. All right. Again, so this is more about polarity. So this is a unequal sharing of electrons, which leads to an uneven distribution of charge. So the oxygens act more negative, as you can remember, like electronegativity from what we talked about on Friday. And while the hydrogens tend to act more positive. So as you can see, it's slightly negatively charged over here, while this is slightly positively charged. And although there are two elements that are charged, water itself actually has a net charge of 0. So basically, water by itself is not charged. However, the atoms in themselves would probably when you charge, and that's because there's a positive end and a negative end, so those two would again cancel out. Next, another very important property would be cohesion and adhesion. So sorry, my mouth is very dry. The cohesion is the attraction between particles of the same substance. So like, again, I know I'm using water as an example for a lot of these, but these are properties of water. So so cohesion is the attraction between particles of the same substance, and it results in other properties such as surface tension. So um over here you have this little cartoon thing. So you can see that the cohesion and the two water molecules are being like attracted to themselves. While adhesion is something also very important, and also you might get a bit confused because I know I did when I first learned about this. So adhesion is the attraction between two substances. So over here you can see that the this water molecule is actually like also being attracted to whatever this thing is. So one way you can remember it is cohesion is like co. So if you like say co-workers, with that would be like among themselves. while adhesion is more like adheres to. So think of it as like this will adhere to another object. Um, so okay, there's a spelling issue that's supposed to say used. I don't really know what happened, but some like important applications of chromatography are like in sorry of adhesion are in like chromatography where it's a really cool experiment that you guys can actually try by yourself where you take a cup of water and like a marker and a piece of coffee filter paper and you can go and put a dot on the paper and dip it in water and watch the water actually move up the filter paper and it will separate the color the parts of the ink inside the marker. So water will form hydrogen bonds with other surfaces in adhesion. So for example, grass, cotton, which is also spelled wrong. Yeah, soil, tissue, etc. So next we're going to see about capillary action. So this is another picture of what I was talking about with chromatography. This allows water to climb up surfaces because of that adhesion property that it has. So this is also responsible for water traveling up plant stems, and it can be used in paper chromatography. So like where the water actually travels up the chromatography or filter paper. So to be more specific on this, like you would put this paper with like dots of ink down here, and the water would separate the ink while it sits in there and while it travels up the filter paper. All right. So, water is actually less dense as a solid. So, as a there's another like practice question or somewhat. Which so say if this picture was picture one and this picture was picture two, which one do you guys think is water and which one is ice? And then which one is more dense? And you guys can just answer that in the chat and I'll give you guys 2 minutes to do to answer this question. All right. Also, if you don't know, you can just put like I don't know in the chat. Okay. So, all right. It's been like 1 minute and I don't know. Do you guys want more time or okay. Well, it's like 2:29 now, so I guess I'll you guys answer. So, this one over here is actually water. And um this picture over here is the ice. So, if you guys remember the like the thing where yesterday where I said like solids can be crystalline or solid, sorry, or amorphous. This one is an example of a crystalline solid because it's in all of like a very organized repeating pattern. While this one is water. So again, with this like the words up here, we would say that this one would be water because it's more packed together and more dense, while this one over here is a is like ice because it's less dense. You can see that there's like holes together and um the water molecules are like farther apart from each other. Okay. Um so this is a very important concept. Oh, also, one of you guys just raised your hand. If you guys have any questions, just I guess put them in the Q&A. And I will actually be watching chat right now because I expected earlier I expected it to come in through as a notification, but it didn't. Okay, so this one is um okay, someone in the chat asked if you could tell from structure 2 that it's ice. In this case, yes, because it's in this like crystalline form. And then somebody also said in the Q&A if it's the same for um other substances. I guess it would depend. It would be like it depends. Um some but I think usually like frozen something frozen so containing water, yes. I'm not super sure about oil. I've never actually really thought about that, so that's a really good question. Um, but I I think I would assume so, yes. However, um, for some substances, it might not be. Okay, so this is very important to biology as in so for example, you have a pond and then like it freezes over. If the ice sunk to the bottom, it would crush all the fish and then there would be no more fish. So and everybody would be very sad. All right. Um, okay, so over here next we have types of solids. So over here we have um the ionic solids, which is more of what we're going to be focused on today. And this is formed by cations and anions. You remember the positive and negatively charged atoms. And they're usually between a metal and a non-metal. So you remember salt again for a common example. Um, this would be like the metal would be the sodium, while the non-metal would be the chlorine, and it would actually form a crystalline shape between the positively charged and negatively charged um, atoms. So, like for example, over here, this would be like the negative chlorine, while this would be like the positive sodium. And these all have very high melting points and boiling points because if you remember, um, those ion bonds are really hard to break. So when you heat them, it'll take longer than say like water, which has hydrogen bonds between the molecules, um, to melt or boil. And while these are very poor conductors while solid, they're very good conductors while dissolved. So for example, like salt by itself in its solid form is probably not very um, conductive. However, they are very brittle. So somebody asked, and how can they be very strong and very brittle at the same time? So the strong in that case doesn't really refer to like the brittleness. So um, it means that the bonds between the molecules are very strong. So it makes them very resistant to being boiled or melted. However, like with an external force, so like um, in this example over here, a hammer, it's easy to like rip these two like two parts of the like what's it called? I'm like blanking out today, sorry. The two parts of this substance apart. Okay, so next is changes in states of matter. I know we did talk about this a little earlier in the presentation, but so when you change a state of matter, you want to like energy is involved, or like you won't be able to change states of matter of something if there's no energy applied. So in this one, energy is involved in phase changes and it's calculated by using heat of fusion or heat of vaporization. So for example, in heat of fusion, that's basically the amount of heat required to change 1 gram of a solid into a liquid. So like, say for example, water again, the heat of fusion of water would be the amount of that would be required to change 1 gram of ice into water. And then vaporization is a pretty similar concept, except for it's between gases and liquids. Um, So that would be, um, so if you have endothermic, sorry, if you would have like 1 gram of a liquid, uh, it would be how much heat it would be that would be required to change that into a gas. All right. Next, we're going to talk about vapor pressure. So the vapor pressure is the tendency of a material to change from a liquid to a gaseous state. This increases with temperature. So over here, as you can see, it's exponential, but it still increases with the temperature. The temperature, it's also the temperature at which the vapor pressure at the surface of a liquid becomes equal to the pressure exerted by the surroundings, which is that's like the boiling point. So at like one point when the basically when the liquid starts turning into a gas, that would be called the boiling point. Okay, I think should be the last couple of slides, and then we can move on to the Kahoot, which is pretty long. So the in evaporation, which is probably like just a review for you guys, molecules break away from the surface of the liquid to become a gas. This requires heat to occur. So, for example, over here, which is like basically the water cycle, um, the heat from the sun would. Here, um, let me just fix that real quick. I'm sorry about that. So, the heat from the sun would heat up the water over here, and then it would turn into a gas. Next is condensation. This is basically a change from a gas to a liquid. When the gas gets cooled down enough, it will condensate and turn into a liquid back again. And then sublimation, again, pretty similar concept. However, this is when like a solid gets converted to a gas. So for example, in this dry ice, you have this block of ice and it's over here, it's instead of melting into water, it's actually just like releasing gas. I think this one should probably be the last one. Um, this is like a gas to a solid. So basically, in terms of like that, it would be sort of like making the dried ice. Okay. So now I guess we're gonna move on to the Kahoot. I hope we have time to finish it. Tried to go a little bit faster so we could get to the end of that, but I don't really know how possible that is. And again, you guys can email me if you have any questions about the class or anything else just in general. All right. Um, so here's the Kahoot. I'm gonna uh, okay. So here's the okay. The code should be coming up in a couple of seconds, and I guess I'll just give you guys like 2 minutes to join. However, if you want more time, just let me know. Okay, I think I'll give you guys more time to join because there's like there's only like let's say 8 of y'all, and then there's 28 people. Sorry, 27 participants. All right. Does anybody else need more time to join? Or also, if you're not in the Kahoot, you guys should join. It's fun, and you get bragging rights if you win. So, all right. Does anybody? If nobody else needs more time, I guess. Okay. If you guys, I'm just gonna start it now, and then if you guys can like, I guess, ask me for the code later. All right, not gonna lie, this is going a little bit faster than I expected, but that's like Oh, my bad, sorry. Alright, so we're going on the podium, and then after this, either you guys kind of like a 2-minute break, or I guess like Bill could start his Alright, um, great. So congrats on whoever won. If you guys have any questions, just email me, and I guess you guys can have like a 2-minute break for the rest of this class. And then I'm just gonna give host over to Bill, and Bill can just like take going from there. All right, great. Thank you guys so much, and bye.